Well, I didn't really expect such a glorious introduction, but I feel humbled. Yeah, thank you for the organizers for organizing this very stimulating workshop, and also giving me this opportunity to speak, especially as a colloquium. And yeah, I have visited KAIST some years ago, but this is my first visit to this IBS in Daejeon. And I'm particularly happy to be able to come here with my bike. I'm commuting every day along this nice river. So we are now in this building, I think. Okay. So yeah, today I'd like to tell you some story about SPT phases, that is symmetry-protected topological phases, and duality point of view. So I'm afraid that some of you guys have already had essentially the same talk elsewhere. So feel free to take a nap or leave. But yeah, for some people, I think this is new. Okay. So yeah, before entering the main subject, I also want to mention that yeah, recently just in this October 4th, we lost Ian Affleck, my postdoc advisor. So yeah, he was only 72, so I didn't really expect him to leave so early, especially because uh, you know, Jung Hoon just mentioned that I like cycling and climbing and so on. And now maybe many people regard me as a kind of outdoor person, but actually I wasn't. I was more like an indoor nerd. But after doing postdoc with Ian in Vancouver, he took me to many hiking and so on. So yeah, now I love outdoor, largely thanks to Ian. Um, and he was maybe 16 years older than me, but he was very fit. So when we went to hiking, I was always struggling just to follow him. So yeah, I cannot still believe that he's gone. Yeah. So I have many memories about him, which I can spend hours to speak. So instead of talking those episodes, yeah, I'm trying to write up my memories. Still work in progress, and I'm also talking with some few other colleagues to publish some form of online special volume for Ian. So if you are interested in contributing, let me know later. So we haven't fixed details, so I cannot announce yet, but hopefully we will make something. Okay. So yeah. So my talk basically consists of two parts. So the yeah, everyone, I think uh, at least people in this workshop knows about SPT phases, symmetry-protected topological phases, to some extent at least. But and it's relatively new subject. It started officially in 2009, but actually there is a long prehistory of SPT in last century. I mean 20th century, and I will discuss what was known about what we call now as SPT phases back then. And then in the latter part, I will discuss more recent progress based on this old idea, duality idea developed in 1990s with my former student, Lin Hao, and also my former postdoc, Yun Jin. They both left my group already. Lin Hao is now in Ghent, University Belgium, and Yun Jin went to Stony Brook, and recently he took a faculty position in Kavli Institute for Theoretical Sciences in Beijing, China. Okay, so yeah, okay. So for many people, probably I don't really need introduction, but still, this is supposed to be colloquium. So I will discuss briefly what is symmetry-protected topological phases. So this is some kind of topological phase. So which means this is non-trivial phase in some sense. But this is not like a conventionally ordered phase. That means that this SPT phase does not have spontaneous symmetry breaking, at least in the usual sense. I will come back to this point later, but so for example, in the ordered phase in Ising or Heisenberg magnet, spins are pointing to the same direction, breaking the symmetry spontaneously, but that kind of thing doesn't happen in SPT phases. So that also means that there is no local order parameter which can characterize this SPT phase. But as I said, this is still non-trivial phase, so you can distinguish this from trivial phase. But by SPT, we mean that this topological phase is distinct only in the presence of certain symmetry. So if you break all the symmetries, then you cannot distinguish this SPT phase from the trivial phase. More concretely, you can start from some trivial phase and connect to this SPT phase adiabatically, that is without crossing any phase transition if you break the symmetry. But if you keep the symmetry, then starting from the trivial phase, in order to enter this SPT phase, you have to cross the phase transition somewhere. So that's a general definition of this SPT or symmetry-protected topological phases. And often this SPT phase is also accompanies edge state, which is experimentally very important because if you just look at the bulk, at least in terms of usual physical quantities, you cannot distinguish SPT from trivial phase. But often you can find an edge state at the edge of the system or surface of the system, which can be detected. And so by now, this study of topological phases has a long history. But I think at least this topological quantum phases started from discovery of quantum Hall phases in 1980s, around 1980. And then after some time, topological insulators were discovered theoretically in 2005. Then after that, there is an explosion of research activity on topological insulators. And actually, topological insulator is a special case of SPT. So this is roughly a free fermion version of SPT. So this is just an insulator which looks boring, but it is distinct from trivial insulator, and it has an edge state. But this edge state or this topological nature is only robust in the presence of some symmetry like time reversal symmetry. So if you break the time reversal, then there is no essential distinction between topological insulator and trivial insulator. So historically in 2005, first this topological insulator or free fermion version of SPT was found. Then few years later in 2009, SPT phases was proposed first by Zhenchen Gu and Gu and Wen. So this is, I guess, official version of history. But as I mentioned, actually long before this discovery of topological insulator, there is a lot of activities related to this concept of SPT. So I would call this as a prehistory of SPT phases.
Masaki?
Yeah.
Can you just ask briefly, can you remind us, quantum Hall, is it just the U1 conservation, or what is the symmetry that protects it?
Yeah, that's important point. It's a shame, but I am still kind of confused. Yeah, this quantum Hall system is, usually we have U1. But if I understand correctly, for example, if you realize fractional quantum Hall state, which has topological order, then this topological order is robust even without U1. That's my understanding. Maybe I'm wrong, but
Okay.
yeah. So yeah, then so this is about the classification of general quantum many-body systems, and this is also related to previous talk by Haruki. So we want to classify quantum many-body systems, and the first thing you do is look at the low energy spectrum. And in some system, okay, so basically every quantum many-body system, at least stable ones, have the ground state. And in some system, you have a unique ground state. There is only one ground state, and then continuum excited states, but they are separated by gap. So in this gap region, there is no energy eigenstate. So if you have this, then you don't have so-called topological order. So this can be a trivial gap system, like a trivial insulator, but this can be also SPT. If you don't have an edge, then ground state of topological insulator or SPT phase is unique. But sometimes you also find a degenerate ground state, also separated from continuum of excited states by gap. And in this case, this ground state degeneracy may come from the spontaneous symmetry breaking, or this may be a topological degeneracy due to topological order. And finally, large class of quantum many-body system belongs to this, has this kind of spectrum. So just above the ground state, you have continuum of gap excited states. So this is called gapless, which includes metals or semi-metals. And recently, also gapless variation of SPT phases are considered. This also belongs to this class. But most basic kind of symmetry-protected topological phase has this spectrum in the absence of edge. So I first consider this class of system. And yeah, as I mentioned, actually the prehistory of SPT phases started long before the discovery of topological insulators. And I think it actually started with this famous Haldane conjecture given in 1981. So again, this is very famous, but to explain briefly, Haldane considered this a very fundamental model in quantum magnetism, that is one-dimensional Heisenberg antiferromagnet. So spins are aligned on a chain, and they are interacting between just nearest neighbors with Heisenberg exchange with a positive J, so exchange is antiferromagnetic. So in the classical limit, the ground state is just a null state. But for quantum spin, there is a quantum fluctuation. So this quantum fluctuation destroys the long range order. Even that is not so trivial as Haruki discussed. But anyway, at least for this antiferromagnetic model, the long range order is known to be absent. And in fact, the spin 1/2 version was solved by Bethe and Zatz long time ago, starting 1931. But to read off physical properties from Bethe and Zatz exact solution is not so simple. So it took many years to figure out what is actually happening for spin 1/2 version. But by before this Haldane conjecture, by 1980, it was known that for spin 1/2, this model has a gapless spectrum, so the continuum of excited state just above the ground state. And also corresponding to this gapless spectrum, the spin-spin correlation function decays according to power law. So in field theory terminology, the behavior of this model for spin 1/2 corresponds to massless field theory. And apparently, before this Haldane conjecture, most people, especially condensed matter people, believe that the essential property of this model should be the same for any spin quantum number, because they just knew what happens for spin 1/2. And at that time, by now, if you are interested in this kind of model, you can download some software and obtain the spectrum of this model up to fairly large system by DMRG or quantum Monte Carlo. So you can see this kind of property in a few hours by doing some simulation. But back then, this was not so trivial. So anyway, so in famous conjecture, Haldane suddenly declared that the property of this model is fundamentally different between half-odd integer spin, like a 1/2, 3/2, 5/2, and integer spins like a 1, 2, 3. And according to this conjecture, for half-odd integer spins, the property is essentially similar to spin 1/2 case, gapless spectrum and power law decay of spin-spin correlation function. But for integer spin, this model is rather described by massive field theory, which means that there is a non-zero gap about the ground state, and the spin-spin correlation function decays exponentially. So this is like a critical, quantum critical behavior, and this is off-critical, really disordered behavior. And initially, few people believed in this conjecture because this was against the common sense at that time. But over time, there are many theoretical and experimental and numerical evidences for this conjecture. So by now, this is almost established. And one of the theoretical support or evidence came from this another famous AKLT, Affleck-Kennedy-Lieb-Tasaki model in 87 or 86. So for spin 1, the Hamiltonian looks like this. So this is a standard Heisenberg anti-Fermat. But they added this biquadratic term with coefficient 1/3. Then for this model, the ground state can be obtained exactly, and it can be pictorialized like this. So this picture means that this dot represents a spin 1/2, and then this solid line represents a singlet pair of two spin 1/2s, up, down, minus, down, up. So without this circle, this dot and bond just represents a completely dimerized state of spin 1/2s. But then you apply this circle, which represents the symmetrization of wave function of two spin 1/2s. Then if you symmetrize, then you project onto triplet sector. So each circle now represents some state of spin 1. So this picture actually represents a certain legitimate quantum state for spin 1 chain. And it can be easily shown that actually this state is exact ground state of this model. And also spin-spin correlation function can be calculated rather easily, and it shows an exponential decay of correlations as Haldane predicted. And also it takes more effort, but people also prove that this is a ground state, but this model has a finite non-zero gap above this ground state, and the continuum excited states is above the gap. This is also proved. So basically, the main points of Haldane conjecture was proved rigorously for this slightly modified model. And you can expect that the original Heisenberg model has similar property to this model, which was also confirmed numerically too in several respects. Okay, so yeah, this played an important role as a supporting evidence for Haldane conjecture, but this was not the end of the story. So yeah, people in 80s, 90s also consider this kind of model. So this is now a Heisenberg chain plus anisotropy term. And this so-called uniaxial anisotropy term is also important to apply this kind of model to real materials, because the experimental realization material like so spin 1 can be often realized in terms of using a nickel 2 plus ion. But this ion often usually have this kind of anisotropy. So if you model some spin 1 chain material, then the model often includes this term. Okay. And of course, in experiment, if you fix a material, then each material has some fixed value of this parameter d. But for theorists, you are free to scan the value of D. So people also consider changing the value of D. Then at D equals 0, this is just a standard Heisenberg model. So according to Haldane's conjecture or prediction, you have a finite gap, which is called Haldane gap. And if you send D to infinity, then basically you penalize SZ equals to plus minus 1. So the only state left in the low energy sector is this product of SZ equals to 0 state. So trivially, you have a gap in the limit of D goes to infinity. And this state is often called large D state, so this region is called large D phase. So in both limits, D equals 0 and D equals infinity, you have a gap, and apparently there is no long range order. Spin-spin correlation function decays exponentially. So naively, we might expect that both sides look similar, so they are adiabatically connected. But when people study this model numerically back in 1980s, 90s, actually they found that the gap closes at certain point. So value of D is roughly 1.0. And actually at this point, the spectrum becomes gapless. So this looks like a quantum critical point, a quantum phase transition. So the existence of this quantum critical point implies that actually this side and this side are distinct quantum phases. Even though there is no spontaneous symmetry breaking, there is no local order parameter. So people did call this side as Haldane phase and this side as a large D phase. But initially, it was not clear why we have this quantum critical point, or quantum phase transition, even though both sides don't have any order.
I'm sorry, I'm embarrassed to ask you this because I
Yeah.
know we discussed it, but I've forgotten what the answer is. What about the gapless XY phase on the, as you decrease D, you could have a gapless phase. And
Yeah,
for
but
Haldane,
it somehow doesn't occur for spin one.
doesn't happen for spin one?
Not for spin one, at least for this model. If you introduce XXZ type anisotropy, then you can realize XY phase.
I see. So there's another axis here, which will introduce a
But
phase.
for spin 2, spin 3, if you consider same model, you have intermediate XY phase.
Okay.
Yeah.
But then there's an interesting question of Haldane into that gapless phase transition.
Yeah. So, well, but as long as Haldane phase and trivial phase is separated by either quantum phase transition or gapless phase, they are still distinct.
Yeah, sure, of course.
But eventually, we find out that for even spin quantum number like 246, this Haldane phase is essentially same as a trivial. Yeah. But for odd integer spin, this is still distinct. Okay. Yeah. So this people already realized, but back then it was not very clear why there is a transition and why they are distinct phases. But now we know the answer. So the current understanding is that this side, so-called Haldane phase, is one of the SPT phase, the topological non-trivial phase. But this side is really trivial phase. But yeah, so back then it was not clear what was going on. Yeah, so I'm showing, okay, so this is perhaps not the first paper. This is already 96, but for example, in this paper, these people study this model numerically. So we can ignore alpha for the moment, but they change the D. So alpha equals 0 is a regular uniform chain. And by changing D, you can find the Haldane gap phase and this trivial large D phase, which is separated by quantum phase function. So yeah, people did find this phase function. Okay. So the Haldane gap phase, at least for spin one, looks like a distinct phase from trivial phase. But what makes it distinct from trivial phase? So again, the clues came from the AKLT state. That is exact ground state of the AKLT Hamiltonian. So people also realized that this AKLT state has two peculiar features. One is the edge state. So as I described, for AKLT Hamiltonian, you can write down the exact ground state, which is actually unique ground state, but only for periodic boundary condition. So if you consider open chain, so this is a left end of the chain. And in order to construct a ground state for AKLT Hamiltonian, you still need to make a singlet pair like this, then symmetrize. But at the end of the chain, this guy, this spin 1/2, does not have a partner to form the singlet. So this spin 1/2 remains free. So in other words, for AKLT Hamiltonian on open chain, this state is still the ground state, whether you choose this spin to be up or down. So this, in other words, there appears a free spin 1/2 at the end of the chain. So this is a edge state for spin 1 Haldane chain. And for AKT model, it's easy to see this existence of edge state exactly. But then in 1990, Kennedy, who is a K of AKT, did some numerical calculation to demonstrate that this edge state also survives in the, for example, in the standard Heisenberg chain, away from the AKLT model. Okay, so this seems to be a feature of the Haldane gap phase beyond the special model of AKLT. And also another peculiar feature was found, that is so-called non-local string order parameter found by Denise and Rommels in 89. So this goes as follows. So this is an AKLT state, but you can expand AKLT state in SZ basis, SZ diagonal basis. And suppose you have a SZ equals to +1 at this site, then both of spin 1/2 should be pointing up in order to make this SZ equals to +1. Then this guy must be pointing up, yeah, both must be pointing up. Then because this is singlet, so this spin 1/2 must be pointing down because this is already up, up, down, minus, down. So this is down. So at this side, because this guy is already pointing down, you cannot make S equals to +1 here. Because at most you can make S equals to 0 by choosing this guy to be upward. Okay. So let me choose this as up. Then this is S equals to 0. But the next one, the same logic, because this was already up and this is singlet, this must be pointing down. So again, this side can have S equals to 0 or -1 and not 1. So if you choose, okay, so then and the same here. So because I chose this as up, then this is down. And if I choose this spin 1/2 to be downward, then finally I can have, then I can have S equals to -1 here. Then after that, now up and down is reversed. So now this is down, so this is up. So you cannot make this side to be S equals to -1. Either 0 or +1. So if you choose this as 0, then now this is down, then next is up. So you cannot make this -1. So by this logic, you can see that once you have +1 here, then you cannot have +1 in the neighboring sites unless you have a -1 somewhere. And you can sandwich any number of 0 in between. But if you remove zeros, then +1 and -1 should alternate. So this was sometimes called a hidden anti-fermionic order because plus and minus alternates. But because you can insert any number of 0, you cannot detect this kind of order by standard spin-spin correlation function. Instead, you can try to count the number of zeros or ±1 by inserting this kind of string operator between SC and SC. And if you define this kind of correlation function, then this remains non-zero in the long distance on AKLT state. And again, people verified numerically that this non-local string order parameter survives also in the standard Heisenberg model of spin 1. Yeah, so okay, so this is a Kennedy's numerical calculation showing the existence of edge state for a modified model. So beta equals to -1/3 is AKLT, but also for other values of beta, this edge state survives. Okay, and okay, so this is the nice Romero's paper proposing this string order parameter. Yeah, back in '89, and also, yeah, there are many numerical verifications, but this was one of the papers which verified that this Denice-Rommel string order parameter survives also at the Heisenberg model for spin 1. So this is a standard spin-spin correlation function. Okay, so they did exact diagonalization up to, I forgot, maybe 14 sites or something. But standard correlation function seems to decay exponentially. But this string order parameter seems to reach some constant. So this implies this long range order in terms of the string order. So also at the Heisenberg point. So this suggests that the string order parameter works as a kind of order parameter, not just at the AKT point, but for a wider range of Haldane gap phase. And I mentioned this paper partly because yeah, they did mention something interesting. That is, they call this hidden topological order. So yeah, they called this spin one Haldane gap phase as some sort of topological phase or hidden topological order phase, using the analogy to quantum Hall state or something. But I have to say that back then it was not clear in what sense this Haldane gap phase was topological. So they did say it's topological, but it wasn't clear in what sense it was topological. Okay. So then there is another important paper by Kennedy and Tasaki, KT of AKLT. So before this paper, people knew the existence of edge states and also this long-range string order. But there are several questions. One of them is that this edge state and string order look like a very different properties, and whether they are related or not. For example, can you have edge state without string order and vice versa? And another question we had was that, okay, so you can define the string order parameter, non-local order parameter, and you can measure numerically. Okay, then it looks like a long range in Haldane gap phase, but does it really mean anything? Because usually local order parameter is useful because it's local. You can define some non-local quantity which may not vanish in the thermodynamic limit. But if you take some random non-local quantity, then it can show anything. So if some non-local correlation function shows some long-range behavior, but generally there is no guarantee that it can really characterize any phase in any meaningful way. But in this paper, they solved these questions by showing that these two apparently very different properties, that is edge states and string order, are actually consequence of the so-called hidden spontaneous breaking of discrete symmetry, Z2 cross Z2 symmetry, which I'm going to explain. And in this view, you can relate this Haldane gap phase versus trivial phase, this phase transition between these two, to more familiar phase transition between long range order phase or spontaneous symmetry breaking phase and trivial phase. So this is our familiar phase transition, and we can relate this mysterious phase transition to more familiar type of phase transition. Okay. So I'm going to explain what they did. So how it works is as follows. So first they defined some non-local unitary transformation. And yeah, after looking at their paper, I introduced some simplified expression like this. In the original paper, it was more complicated, but it can be written like this. So this is a product of this exponential of SC at side J and SX at side K. But you take a product of this factor for all J smaller than K. So this can involve very non-local term where J and K are very far away. But anyway, you take the product of all such term, then this defines certain unitary transformation. Then if you transform, for example, SZ at side J by this unitary transformation, then you get not only SZ, but also this string running to the left of this operator J at side J. And if you transform Sx, similarly you get a string now running to the right of this side J. So because this is non-local transformation, if you transform this local operator, you get something non-local, which is not surprising. But yeah, so at this point, by doing something non-local, you get something very non-local, which might not sound very useful. But actually, for many Hamiltonians, this turns out to be useful. And also, if you look at this formula, and probably many of you are familiar with Jordan-Wigner transformation between fermion and spin, or fermion and hardcore boson. And there is several similarity between this Kennedy-Tasaki transformation and Jordan-Wigner, although they are not the same. So in Jordan-Wigner, you also get a string. But the point is that, for example, if you consider this Hamiltonian I discussed before, then each term consists of Sx, Sx, and Sc, Sc, and so on. Then if you consider, for example, Sz, Sz within this Hamiltonian, then both of Sz acquires a string, infinitely long string to the left. But because if you get the two strings overlapping, then you get the exponential of 2 pi I times Sz in the string part, but eigenvalue of Sz is integer. So you can ignore this exponential of 2 pi I times Sz part. So that means that most of the non-local string operator cancels. And you are only left with a string of length 1 between these two sides. So from SGSE, you get this term, and you can do similar analysis for SX, SX, and SY, SY. And if you transform this Hamiltonian by this Kennedy-Tasaki non-local Hamiltonian, you end up with this Hamiltonian, which looks a bit strange, but still, local or short-range interaction Hamiltonian, because this only includes a nearest neighbor interaction. So this is still a local Hamiltonian or short-range interaction Hamiltonian we are familiar with. And the original Hamiltonian may have SU2 symmetry or U1 symmetry, but in this transformed Hamiltonian, apparently this continuous rotation symmetry is lost. But still, this Hamiltonian is has a global rotation symmetry, that is discrete symmetry corresponding to pi rotation about x, y, or z axis. Because if you rotate spins, all the spins by angle pi about z axis, then Sx and Sy goes to minus Sx and minus Sy. But here you have a 2Sx, so both gets minus sign, so minus sign cancels. And also in this string part, plus I pi Sx goes to minus I pi Sx. But this difference is again e to 2 pi I Sx, which is equals to 1. So actually this Hamiltonian is invariant under pi rotation about z-axis or x or y-axis. And mathematically, this is equivalent to Z2 cross Z2, which this might look like a Z2 cross Z2 cross Z2, but actually pi rotation about, for example, Z-axis is a product of pi rotation about X-axis and pi rotation about Y-axis. So there are only two independent Z2s. So we can identify this as Z2 cross Z2. And now, so this is short-range interaction Hamiltonian with this discrete symmetry. And the discrete symmetry can be spontaneously broken even in 1D. Okay. So suppose this dihedral symmetry D2 or this Z2 cross Z2 symmetry in the dual Hamiltonian is spontaneously broken. Then what happens is that now in the dual system, the usual spin-spin correlation function is long-range. So this is a usual indication of the spontaneous symmetry breaking. But now you can go from this statement to original system by applying this Kennedy-Tasaki non-local unitary. So if you apply this non-local unitary, then this usual spin-spin correlation function is mapped to this one because both SC gets a string, but when J and K are apart, then the string between J and K are not cancelled. So it remains here. So I get this, but this is nothing but a string order parameter, string correlation. So if the this discrete symmetry is spontaneously broken in the dual system, then this automatically implies that this string order parameter is non-vanishing in the original system. So this looked like a mysterious or unclear quantity, but if you make this mapping, you can relate this to the usual order parameter in the dual system. And there is another consequence that is, again, let's assume that the dual system spontaneously breaks this Z2 cross Z2 symmetry spontaneously. Then, as usual, the ground state of the dual Hamiltonian should be fourfold degenerate. But this Kennedy-Tasaki unitary transformation was unitary. So that means that the spectrum is preserved. So also in the original model, the ground state must be fourfold degenerate. But this sounds like a contradictory because in the AKLT chain or Heisenberg chain Haldane gap phase, the ground state is supposed to be unique. But this mapping, Kennedy-Tasaki mapping, was defined for open chain. Okay, I will come back to this point later, but because this definition requires the ordering of the chain, so we discuss open chain with two ends. So this argument only implies that in the original system, the ground state must be fourfold degenerate only if you consider the open chain. But in the periodic bound condition, you have unique ground state. Then this ground state degeneracy in the original system must be due to the edge state. So in this way, this is a bit indirect, but this spontaneous symmetry breaking in the dual picture implies the existence of the edge state. So yeah, as you can see, so this Kennedy-Tasaki paper was published already in 1992. So back then, we were almost there. I mean, many of the properties now we understand as SPT phases are kind of known. But I have to say that still we missed the very concept of SPT. So why is that? So the reason, in my understanding, is that back in 1990s, we didn't ask a very simple but yet very important question for some reason. So the crucial question we should have asked was, well, I showed this very nice picture of the non-local unitary duality mapping, but the crucial question was when that argument works. So it actually doesn't work for some, random Hamiltonian. But it works nicely for Heisenberg chain, AKLT chain, and Hamiltonian with uniaxial anisotropy. So there is a condition under which this duality mapping works well. And only after 2009, we came back to this question. And if you ask this question, the answer is kind of simple. That is this Kennedy-Tasaki transformation duality picture is useful if the original Hamiltonian has the same global symmetry Z2 cross Z2 or pi rotation about XY or Z axis. Because if this symmetry, if your Hamiltonian satisfies this symmetry, then every spin operator Sx, Sy, Sz must appear in pair, like a Sx, Sx, Sy, Sy, or exponential I pi Sx type. Then for those terms, you can show that if you transform, then non-local part of the string operator cancels with each other. So the dual Hamiltonian is again short-range interaction. So you can use this argument. So if you ask this question, this is the answer, then that implies this following statement. That is, if you require your Hamiltonian to respect this global discrete symmetry, Z2 cross Z2, then, for example, so-called Haldane gap phase corresponds to the spontaneous symmetry breaking phase in the dual Hamiltonian, and the trivial phase corresponds to the trivial phase in the dual Hamiltonian. So if you go to dual Hamiltonian, then SSB phase is clearly distinct from the trivial phase. So this distinction can be brought back to the original Hamiltonian. So that means that this, for example, Haldane gap phase for spin 1 is distinct from trivial phase as long as you respect this discrete symmetry in your Hamiltonian. So this is nothing but the modern concept of SPT phase. But back in 1990s, yeah, we somehow didn't ask this important question, so this was kind of not clear back then. But yeah. Yeah, but that was not essential. I mean, you can break SU2, but as long as you keep this symmetry, then SPT is distinct from, or Haldane gap phase is distinct from trivial phase, and that is SPT. Yeah. Yeah. Actually, it's in terms of symmetry generator, it's the same. Yeah. So yeah. So yeah, by using this old idea of Kennedy-Tasaki duality mapping, actually we can infer the existence of SPT protected by this discrete global symmetry. But yeah, I have to say that okay, so this duality picture is very useful and interesting, but at least in my knowledge, this duality picture does not work for every symmetry. For example, this SPT can be protected by time reversal or spatial inversion, but for those kind of symmetry, I don't know existence of duality mapping like this. So, but at least for some symmetry protecting SPT, we can apply this duality picture. Okay, and yeah, so yeah, because yeah, Haruki also mentioned his first paper, so yeah, maybe not exactly first paper, but so this is a bit a nostalgic subject for me because so this was my first scientific paper actually. So yeah, I went to summer school when I was a first year grad student, and luckily for me, on that year, Tasaki happened to be lecturer, and he gave a very nice course on spin chain, Haldane gap, and then I was interested, and then later I visited his office, and that was like 1990 or 91, and that is just before this archive Condomat started. So archive started in 91, and the Condomat section started only in 92. So at that time, it was not easy to get the preprint. But I visited his office, and he gave me a copy of his draft or maybe preprint. Then I brought back this copy and then played around with this formula and found this compact expression. And so this was also useful in the sense that by writing this Kennedy-Tasaki transformation in this way, this is immediately applied to any integer spin. Actually, this doesn't quite work for half integer spin, but it works for any integer spin. And then in this paper, I found that at least in AKLT state, you always have this duality mapping, and the dual Hamiltonian has the same Z2 cross Z2 discrete symmetry. But this discrete symmetry is only spontaneously broken in odd spin AKLT state, but not in even spin AKLT state. And at that time, I didn't understand what it means, but many years later, coming back to this problem, now it's clear that this implies that the so-called Haldane gap phase is only SPT, symmetry protected topological phase, only for odd integer spin. But for even integer spin, the Haldane gap phase is essentially trivial. Maybe that's what I discussed in Liken when you came to Liken. Anyway, okay. So, okay, that's a very old story. Sorry about that. But, and I almost used up my time. But what I want to say is that, SPT was clearly conceived only after 2009. But before that, long before that, there are many interesting ideas, especially this duality mapping related to SPT. And after 2009, there has been a lot of progress in field theory understanding and so on, so on. So it would be interesting to revisit this duality approach from the modern viewpoint. And that was exactly what we did recently, or more precisely, my former group members, Yunjin and Lin Hao, did. So one thing is that, because this is somewhat related to the theme of this workshop, I mentioned that the Kennedy-Tasaki transformation is only well defined on the open chain, not a periodic boundary condition. That is in some sense correct, but actually not completely correct in the sense that actually you can apply this Kennedy-Tasaki transformation on a link, which we were missing back then, but I realized this only after seeing the results by Lin Hao and Yunjin. So actually the result is very simple. So as I discussed, if you transform SZ operator at side J, you get a SZ at side J, but also this string running to the left of this side. But you can still apply this to the link by choosing, you can number the sides on the link arbitrarily. So you just pick up side 1 to side L. But you get the problem because if you transform SZ at side L plus 1, then you get this string which wraps around the system. And this is a non-local term. So naively, if you start from a nearest neighbor interaction model, but then apply this mapping on the link, then you get this non-local term, which is not cancelled. That seems to be a problem. But if you look this carefully, this string operator actually wraps around the system. And this is nothing but operation which rotates every spin about z-axis by angle pi. So actually, this is one of the generators of this global symmetry, global dihedral or Z2 cross Z2 symmetry. So as long as Hamiltonian is symmetric, every energy eigenstate can be chosen as the eigenstate of this global symmetry operation. Then you can replace this string operator with a symmetry eigenvalue. So actually, it's kind of shame because I have been working with Jordan-Wigner transformation also for many years, and exactly similar situation occurs in Jordan-Wigner. You get if you apply Jordan-Wigner transformation on the link, then you do get some non-local string wrapping around the system, but you can replace that string with a symmetry eigenvalue, fermion parity or something. So yeah, same logic can apply here. So that means that you can apply this to a system on a link, The only difference is that now the new boundary condition may be twisted. Okay, so this is the original boundary condition, and this is a new boundary condition. And the new boundary condition after doing this transformation may be twisted depending on the symmetry eigenvalue of your sector. So yeah, this has two interpretations. One interpretation is that you want to fix the boundary condition for the original spin and dual spin. But then dual spin boundary condition is specified by symmetry eigenvalue. In that case, your pre-specified boundary condition may not match the resulting boundary condition. In that case, you can interpret it that this mapping, just maps to the null vector. So your state just vanishes by this transformation. So this is still viable interpretation, but in this case, this Kennedy-Tasaki transformation on the ring is no longer unitary and not even invertible. But recently, there is a lot of interest in non-invertible symmetry. So if you consider Kennedy-Tasaki duality mapping on the ring, so this becomes one of the such a non-invertible transformation. So generally, this is not a symmetry, but you can also consider self-dual model under Kennedy-Tasaki, in which case this really becomes a non-invertible symmetry. And yeah, another interpretation is that you can introduce this boundary condition untwisted or twisted as some extra qubit. So if you regard this boundary condition as an extra degree of freedom, then you can interpret this Kennedy-Tasaki mapping as a kind of unitary transformation. But anyway, this is very similar to what happens to Kramer's one-year duality. Okay. And also, yeah, what Yunqing and Lin Hao came up
Masaki,
with is...
Could I ask a question?
Yeah, sure.
About this self-dual model? So is it gapless or for
yes, sometimes gapless. But I think it doesn't always imply gapped sector, but well, I thought, but yeah, you can sometimes construct a self-dual and gapless
so
model
is it
under this.
not unique way how it is constructed, or?
Well, it depends on your construction.
Okay.
Yeah. For example, not me, but Hosho, Katsura, and company consider some concerning the two chains, and one chain is mapped to another chain by Kennedy Tasaki. But if you choose appropriate parameter, then this double chain becomes self-dual under KT and so on. So I think just by imposing self-duality, the model is not unique. It depends on your construction.
Okay. Thank you.
Okay. Then, okay, I have to...
Excuse me, I also have a question. So
Yeah.
could you please go back to the previous slide? So we know that Kramers-Wiener duality corresponds to a defect in Ising CFT. So do we know the similar correspondence for the KT duality?
Yeah, I think so, yeah. You mean Kramers-Wanier can be formulated in terms of this defect in...
Yes, in Ising CFT.
Yeah, I think same here, yeah.
It's the same here, okay. So what is it?
Hmm?
So, I mean, what is it? What is it?
What is... okay, so maybe next time introducing the field theory formulation, so maybe you can read it.
Thank you.
Although maybe not so obvious from here, but I cannot recall the short answer immediately, so maybe we can discuss later. But anyway, so in modern or abstract language, the SPT phase is identified with some kind of topological quantum field theory characterized by a partition function as a function of the discrete gauge field, A1 and A2. each of this gauge field corresponds to this Z2, one order Z2 and the other Z2. And so given the theory, you can consider two different manipulations. One is just a stacking Z2 cross Z2 SPT, which is characterized by this partition function as a function of gauge field. So stacking means just take a product of partition function of original system with this stacked SPT. And another procedure is so-called gauging of this symmetry. So original partition function, now this small a1 and a2 becomes sort of dynamical, and you sum over different gauge field configuration, small a1 and a2. And then you can gauge this symmetry. Then you get a new partition function of new theory. And with these two procedures, you can see that these three different phases, trivial phase and SPT phase and spontaneous conventional SSB phase, can be mapped each other. For example, if you gauge trivial system, it goes to SSB. And if you stack trivial phase with SPT, of course, you get to SPT. So this diagram summarizes transition between these three phases by these two operations. And looking at this figure, you can identify Kennedy-Tasaki transformation with the product of this S times T times S. Because if you start from SSB, you first apply S, then goes to trivial, then apply T, stacking goes to SPT. But if you gauge the symmetry for SPT phase, you go back to the SPT. So in the end, you start from SSB and end up with SPT. So this product has the same functionality as Kennedy-Tasaki. So this is maybe the field theory formulation of Kennedy-Tasaki transformation. And one advantage is that now this Z2 cross Z2 symmetry can be implemented on spin 1/2 system instead of spin 1 using the sigma spins and tau spins. So we can identify one of the Z2 symmetry as a spin flip of sigma spins and the other Z2 as a spin flip of tau spins. And then we Yunji and Linhao came up with explicit operations corresponding to this gauging of these two symmetries and stacking with SPT phase using this sigma and tau spin representation. So this looks very complicated, but this is well-defined operation for sigma spins and tau spins. And this does work of this gauging and stacking. And by this, we can define the spin 1/2 version of Kennedy-Tasaki transformation just by taking the product of this S times T times S. So in terms of operator, this N times U dW times N. So this gives you some well-defined version of spin 1/2 version of Kennedy-Tasaki mapping. And let me skip this. And we can, okay, so this mapping looks complicated, but we can, for example, start from this very simple model. This is two independent spin 1/2 Ising chain. So this is completely classical because there is no transverse field term. So of course, the ground state of this model has long range order SSB because the sigma spins and tau spins are independent and both are magnetized in ground state, up or down. So this is almost, this is basically trivial model, but you can apply our spin 1/2 version of Kennedy-Tasaki duality mapping to this model. Then this duality mapping couples sigma and tau spins, which were initially independent. But after the mapping, I get this Hamiltonian, which now couples sigma with tau. So this is more non-trivial model. But actually, this is known as a so-called 1D cluster model. And this is also representative Hamiltonian realizing the Z2 cross Z2 SPT in 1D. So this has been known, but our point is that we can construct this cluster model naturally starting from this SSB model by applying this Kennedy-Tasaki mapping. So the SPT nature of this model is automatically follow from the spontaneous symmetry breaking in this model and the nature of this duality mapping. And likewise, you can introduce transverse field, and it was also known that by tuning this H to the critical value 1, there is a critical point which corresponds to some version of so-called gapless SPT. And if you just look at this Hamiltonian, this looks a bit non-trivial. But if you go back to this more trivial Hamiltonian by Kennedy-Tasaki duality mapping, then in this dual picture, this is just a one classical Ising chain plus another Ising chain, but a quantum Ising chain with a transverse field. So in this dual picture, tau and sigma are completely independent. And only sigma sector undergoes the critical point. And so-called gapless SPT nature of this model can be inferred from this more familiar model. So in this way, something looks like a non-trivial, more non-trivial in this side can be made more simple in the dual picture. And okay, so there are now many variations of the so-called gapless SPT phase, but in the same way, we can start from better understood model like XY chain, XXZ chain, and then apply this duality mapping to construct more non-trivial model which possess so-called gapless SPT phase. So yeah, I skipped the detail, but our point is that okay, so we can start from well understood independent chains like SSB plus trivial. Okay, so this gives same trivial state, but so this is a simplest case. We can start from two independent Ising chain, both in SSB phase. But if you apply duality, you can produce the Z2 cross Z2 SPT phase ground state of the cluster model. But you can also start from some SSB phase plus some critical state, CFT state, and then apply this mapping. Then you can obtain some non-trivial gapless SPT phase, and so on, so on. So yeah, if you just look at the right-hand side, this looks very complicated and non-trivial. But if you go to the dual picture, it's more familiar and well understood. And there are a lot of recent developments. So to conclude, yeah, this symmetry-protected topological phases are distinct from trivial phase, but only in the presence of symmetry. So it means that the entanglement is only short-ranged, but often has edge state, and sometimes characterized by non-log order parameter. And yeah, now this is one of the very active field in physics, but yeah, official history started in 2009, but many of these features were recognized in the previous century, 20th century, in the study of Haldane gap phase. And in particular, this Kennedy-Tasaki duality relates the SPT phase, kind of exotic to SSB phase.
Oh, could we see this picture in any dimension?
Yeah, that good question. So in higher dimension, okay, so I cannot follow all the literature, but at least what I know is that in higher dimension, if you have SPT phase protected by something like a subsystem symmetry or higher form symmetry, then there are some duality mapping similar to this.
So, so by including hyperform symmetry, we can see the picture.
Yeah.
Okay.
Again, I'm not sure if this kind of duality exists for any higher form symmetry, but at least I know at least for some higher form symmetry, you can construct a similar duality picture.
Thank you.
Okay. So this Kennedy-Tasaki duality actually published in 1992 relates this more exotic type of quantum phase SPT to more conventional SSB phase. And so recently, yeah, we are trying to revive this idea, and indeed, many other people are working on along this idea recently. And this may be one of the example of recent resurgence in so-called generalized lambda paradigm. That is, we have been talking like topological phases beyond lambda paradigm, what you cannot understand in terms of lambda paradigm, blah, blah, blah. But once you generalize the notion of symmetry to this kind of symmetry in dual system or higher form symmetry or something like that, then actually lambda paradigm can be enlarged. And in fact, this phrase I found in recent lecture note or something by John McGreevy. Yeah, he claimed like lambda was even more right than we thought, because all those topological phases, once we thought as beyond random paradigm, maybe actually within random paradigm, once you generalize the notion of symmetry. Yeah. Thank you for your attention.
What is a Z2 or Z4 free boson CFT? I thought I knew what free boson CFT was, but I didn't know you could modify it.
Oh, this one. Yeah. Yeah, I forgot the detail, but I think, yeah, this is just, yeah, free boson is free boson. But yeah, we need to choose the compactation radius appropriately to, yeah, to induce the appropriate action of this Z2 or D4 symmetry.
So I have a question about, so you said that from this dual picture, you can infer, let's say if there is a critical point, which is a gapless SPT, like you can infer from the dual picture that it is exactly here. Could you explain a little bit how it is done?
So yeah, so yeah, people did study this cluster model with transverse field, and then well, you can in fact get a lot of information by directly analyzing this model. But anyway, so by analyzing this model, changing this transverse field H or this field H, you can find a critical point separating two gapped phases. And so for this Hamiltonian, for small h, it's in SPT phase. So, okay, so maybe, yeah, I think, yeah, I should better use this slide, because for small h, you are in Z2 cross Z2 SPT phase. So you have H state. So for open chain, you have two degenerate, two from left, two from right. So in total, you have 4 degenerate ground state. But if you crank up H to, let's say, infinity, then you align sigma spins to X direction. So sigma spins are dead. But now this sigma X can be replaced by 1 or -1. Then you are left just with classical Ising chain for tau. So tau Z, tau Z. And the sigma degree of freedom is frozen. So for large H limit, you just have a Z2 spontaneous symmetry breaking phase for tau spins. And the sigma spins are frozen. And people did find a critical point separating this SPT phase and the SSB phase. And here, critical point, but still you see a remnant of edge state. But the remnant is only twofold exponentially degenerate ground state below this CFT like gapless spectrum. And that property is not so simply understood if you just look at this original Hamiltonian. But if you go to dual picture, you decompose this model into classical Ising system plus quantum transverse Ising chain. And just a transverse Ising chain for sigma becomes critical. So this becomes almost obvious once you get to the dual picture. Yeah. This was what I wanted to say.
Can you comment on, if this is known, how the topological properties of the ground states of these models, which you were discussing, are impacting, if at all, the level spacing statistics of the excited states of the same models? Is there some correlation, like these systems are integrable or quantum chaotic?
Oh, yeah, thank you. That's a very important question, but I'm not quite expert on this. Maybe someone knows better. Yeah, because yeah, what I know is that for example, AKLT model, it has gapped ground state, and basically only the ground state is exactly solvable. But there are some special excited states also kind of exactly solvable. And they act like a so-called quantum scar, am I right? So I think the excited state of, let's say, AKLT model, most of them obeys usual level statistics, but there are some special states which are kind of exceptions, which is, I don't know how directly these existence of special states are related to the special nature of the ground state, but yeah, through the Hamiltonian, it's sort of related in my understanding. Yeah.
Thank you.
So, can I understand this group cohomology classification of SPT from the point of view of this KT duality? Thanks.
Yeah, another good question. Yeah, should be related. But yeah, at least for this on-site symmetry should be related, but
So in one
yeah.
view, we use this project representation to classify the SPT. So I think there may be some fingerprint in the dual system. You know.
Yeah. So there must be general relation, but sorry, I don't know. Yeah, that's interesting question. Yeah, if you have idea, maybe we can discuss.
So for the generalized random paradigm, so can we understand that deconfined critically as a kind of generalized random paradigm?
Oh, that's again interesting question, but I don't really know. Well, so deconfined critically itself is kind of controversial, right? Then yeah, if we can construct some general random paradigm for deconfined criticality, maybe we can really establish some examples, maybe. But okay, short answer is I don't know. Maybe some of the audience might know the answer. But yeah, another interesting question, I think. Thank you. 감사합니다.